So my name is Jeremy, and I'm going to talk about some work I've done with Robert Weber. We worked on a gradient-free MCMC sampler targeting function space. First, I'll talk about infinite dimensional inverse problems. The goal, as usual in Bayesian inference, is to infer some parameters from some data. And when we work with ODEs and PDEs, the parameters will often include functions and fields, so infinite dimensional objects. Now, obviously, we'll have to discretize our functions to sample from them kind of on a computer, but we would like MCMC methods that are independent of dimension, so that truly target the function. And there are many of these methods available, but usually involves gradients. The usual starting point is the function space version of random walk, which has this proposal. So X here is the discretization of the current MCMC sample, namely the function, but discretized. Beta is the step size, and chi is a sample from the Gaussian process prior. Now this simple proposal is independent of dimension and corresponds to random walk on function space. If you then have gradients, there are much more efficient samplers than random walk, but in many cases you don't have gradients, so we would like to develop a sampler that's better than random walk, but that doesn't need gradients. And that's what we call the functional ensemble sampler. The general idea is to write out the parameter using a new basis, namely the eigenfunction expansion of the prior. We're going to use this to define two subspaces. Firstly, a low rank approximation to the function, finite dimensional space, and secondly, the complementary subspace, namely the rest. And the idea is to do metropolis within Gibbs on these two subspaces, namely some proposal, that we'll talk below, on the low dimensional subspace, and then PCN, so the functional random walk, on the complementary subspace, and to just alternate sampling on these, and that'll be our sampler. Now, what proposal for the low dimensional subspace? We're going to use the Goodman and Weare Ensemble sampler from 2010. What it does, it defines an ensemble of walkers that targets the product space of the posterior. And the idea is that to update each walker, you choose another walker randomly in that ensemble, and you draw a line through them. And then you either interpolate and move towards the other walker, or extrapolate and move away from it. This is the proposal with some univariate random variable z. This sampler is gradient free, that bit's important, and it has lots of nice properties like affine invariant, scalable, and so on. So we would like to extend this to function space and keep some of these nice properties. So our sampler is exactly that. It's an ensemble sampler, and that alternates sampling firstly on the complementary subspace using functional random walk, namely PCN, and secondly uses this ensemble sampler, this Goodman and Weare ensemble sampler, on the low dimensional space. And it just alternates sampling on these two. And that's our sampler. We then try it out on a numerical example. We try it out on path reconstruction for Langevin dynamics, and these are the equations. And we want to infer these two scalars, alpha and sigma, as well as the posterior paths xt, namely functions. And we have noisy observations of position xt. So that's our sampling problem. We're going to generate some observations from a sine wave, so there's going to be a model misfit, which makes the problem harder. And we set up some priors. We're then going to compare the following algorithms. Firstly, standard PCN, so Gaussian proposals for the scalars and PCN for the path, an alternative gradient-free sampler in the literature, and finally our functional ensemble sampler with a few settings. For example, with a few walkers or with many walkers, 100 walkers, to see how it performs. Before showing the kind of performance, we show the posterior here for the two scalars and for the trajectories. Here we see some multimodality alpha and some multimodality in the frequency of the paths. And the values of alpha determine the frequency of the path, so these are correlated. And this is quite a challenging sampling problem. There's a lot going on. Finally, here are the results. We have the ACF plots for the two scalars, and we can see that our functional ensemble sampler with 100 walkers, both versions with 100 walkers, works the best, decorrelates much faster than the other ones. So our ensemble sampler is much more robust to this mild multimodality and model misfit. So in conclusion, we have a new gradient-free samplers that enjoys some nice properties. And excellent, that's everything. Thanks very much.